Alright, in this video we want to make sense of how directional differentiability and partial differentiability follow from a total differentiability of a function f, where f is a mapping from r to the power of n to r. Okay, so consider the function f going from r to r, so just a single variable case for now. Here's the graph of the function, and we know that the function f is differentiable in a point x0, here's x0, and if we have this limit here, as x goes towards x0. Now we have called this limit just simply to be this expression. And the way we approach this now is we want to find an alternative definition for the differentiability of a function in a point x0. And for that we consider the tangent line. So let us consider the tangent line in a point x0. So we have here the tangent line, let's call it t of x. And we know that the first derivative of f of x in the point x0 is nothing else but the slope of the tangent line in this point x0. So this whole business here equals to the slope of t of x, which is delta y over delta x, where, if we take a look again here, this graph, our delta y consists of these 2 points. So our delta y is equal to t of x minus f of x0 over our delta x, which stays the same as above here, which is nothing but x minus x0. So here's delta x and here's the delta y. Okay, so now we can reformulate, or we can just solve this business here. So that expression and this one, that expression and this expression we can reformulate to get the equation for our tangent line. So it would be t of x equals to the first derivative of x in x0 times x minus x0 plus f of x0. This expression now gives us the equation for a tangent line. Okay, now that we have our tangent line, let's introduce another function. We call this function psi of x, and we'll have psi of x be equal to f of x minus t of x. Now, so if you take a look at this graph, psi of x is nothing but the distance here between f of x and t of x, or the gap if you want. Now if we solve this for t of x, we would get, this is equivalent to t of x equals to f of x minus psi of x, and inserting t of x now here into the equation of our tangent line will give us the following result. F of x is equal to the first derivative of f in the point x0 times delta x, which is x minus x0, plus f of x0 plus psi of x0. So now we can say a function f is differentiable in the point x0 if we can find such an approximation, of this function. Okay, now let's examine the behavior of the psi of x. We can find, let me just write the equation again here. F of x is equal to f of x0 times delta x plus f of x0 plus psi of x. Now as x goes towards x0, this psi of x here approaches 0. So psi of x goes towards 0 as x approaches x0. And how do we show this? So let's get this here onto this side of the equation. Then we would have f of x minus f of x0 that's equal to the first derivative of f and x0 times delta x, which is x minus x0 plus psi of x. So now we let x run towards x0, then we can see that if we have this case, then this expression here becomes 0, and hence this whole product here is 0. And as x also approaches x0, f of x approaches f of x0. So what we have here then is f of x0 minus f of x0, which makes this whole expression to 0 as well. Then what we are left is 0 equals to, that's an equals to, not a plus. 0 equals to 0 plus psi of x. So psi of x is equals to 0. Shown here. And furthermore, actually, we can say furthermore, not only does psi of x approach 0 as x approaches 0, but also the limit of as x goes towards x0 of psi of x over x minus x0 is also 0. Now how do we show this? In a similar fashion, maybe I don't want to write this whole thing, so what we just do here, we divide by this delta x here, and then we get this first derivative of f and x0 over onto this side of the equation. So what we're left with then is f of x minus f of x0 over x minus x0 minus the first derivative of x and x0, which is equal to, now we divided by x minus x0, so both, so we have to divide it here as well on this summation. So psi of x is also divided by x minus x0. Both sides have to be divided in this equation. Okay, so if we now what we can do is we can take the limit on both of these sides. The limit as x approaches x0. Taking both these sides, what we would get is, just copy this on here and this part down here, maybe a bit more space. So now we have the limit of this here as x goes towards x0, and the limit of this whole part is just the limit of this part minus the first derivative of x and x0, and this whole business is equal to the limit as x goes towards x0 of this expression. So what we have here, this is basically nothing else but this part here. So this whole limit is equal to this, because that's just the definition of the first derivative of the function. So what we are left with is the first derivative of f of x0 minus the first derivative of f of x0 is equal to this limit here, but that's just the same subtracted from the same, which is 0. So what we have now is, as we let x run towards x0, psi of x goes towards 0 is equal to 0, and also the limit as x goes towards 0 psi of x over x minus x0 is equal to 0, meaning that this whole part here runs faster towards 0 than this delta x below. So what we have so far is we have this approximation of a function here, defined the following way, with psi of x is 0 as x approaches x0, and furthermore the limit of psi of x over x minus x0 as x approaches x0 is equal to 0. Now what we're going to do next is we will redefine x. So this x here, inside here, this function, we will redefine it to be x0 plus some other number h. Now this will yield the following, or this will change the function the following way is, we get f of x plus f of x 0 plus h equals to the first derivative of x0 times h. Now remember, h is simply x0 plus h minus x0, and this was our x before. So our x minus x0 just got to x0 plus h minus x0, which gave us h. So then we have the first derivative of x0 times h plus f of x0 plus psi of x0 plus h, where the limit as h goes towards 0 this time of psi of x0 plus h is equal to 0. So now that we have boiled down everything to this expression here, we want to take a look at the multivariable case where our function f goes from r to the power of n to r. And remember, what we want to do is we wanted to find an alternative expression for the total differentiability of a function, or just the differentiability of a function, and use that to derive directional differentiability and also partial differentiability. And what we have here is almost the definition of the total differentiability. All we need to do is change this product here. Now, a function f is totally differentiable. Now, so let's first consider we have f from r to the power of n to r, so that means x0 is a vector, is some n-dimensional vector here, and h is also some n-dimensional vector here. Now, the case that x0 and h are vectors, that means the limit, as we tend x, if we let x go towards x0, of f of x minus f of x0 over x minus x0 is not defined, because the division of two vectors is not given. Alright, so like I said, we have almost here the total differentiability of a function. We just replace it, replace this part, and that means so a function f is totally differentiable if there exists in A and A is an n-dimensional vector, so A1 dot 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 till AN, such that this whole expression looks the following way: f of x0 plus h is equal to the scalar product between A and h plus f of x0 plus psi of x0 plus h. Okay, now this is definition of total differentiability of a function that goes from r to the power of n to r. Now we will derive total direction differentiability from this simply by redefining h to be equal to some number alpha times our directional vector v. Now, where the norm of v is equal to 1. So what we then have is f of x0 plus alpha times v equal to the scalar product between A and alpha times v. Maybe I should denote this. Yeah, right. Anyway, maybe I should denote this as an open circle for the scalar product. This whole thing plus f of x0 plus psi of x0 plus alpha times our directional vector v. Okay, what we need to do in the next step is we will simply, now this is not an A, this is an alpha. Maybe it's a bit too messy, but you get the idea, it's an alpha. So what we need to do is we bring this to the left side of the equation and then we divide by alpha such that we get from here f of x0 plus alpha times v. Now it's a small v, it's v minus f of x0 divided by alpha, and that's supposed to be equal to the scalar product between A and our directional vector v plus psi x0 plus alpha times v. Okay, now if we take the limit on both sides, then you will see that now we just take the limit on both of the sides. I just copy it over here and copy this part over here, a bit more room. So now we take the limit, namely as alpha goes towards 0, then we can see that this part here is already the definition of the directional derivative. That is equal to A scalar product between A and V plus the limit as alpha goes towards 0 of psi of x0 plus alpha times V over alpha, sorry. I should have done that, and I should have done it here. Here's also an over alpha. Okay, so now remember that this limit here is 0 from what we have discussed previously, and this is just the definition of our direction derivative with respect to our directional vector v. So in total we get this here equation. Maybe we can denote the +0 here. So now you've seen that from total differentiability we can derive direction differentiability, and now from direction differentiability we can derive partial differentiability simply by redefining our direction vector v to be equal to some base vector e of this form, where 0 is everywhere else except for the ith entry there is a 1, and then 0. And also you can see that the norm of this vector of ei, the norm of it is actually equal to 1.